All right, I'm going to click this and see what happens. I'll stop my share here. Cool. So at some point, this will actually go live. And by the way, I think there's a very good probability that 0 people are watching, probably 90% chance. So, yeah. So basically, this is the second time we've done this, but the idea is just to kind of get a feel for how things go. How we think at Saleae, kind of what how we do things, and it's going to be very low production value and casual, and we'll get better at it over time. But it'll be just fun, and then ideally, it's one thing I think about is like if candidates end up like you want to, let's say you're going to join the engineering team or the software team or something like that, right? And they want to be like, well, what the heck kind of technology are you using? What's the workflow? What's it like to talk to these people? That kind of thing. That might be kind of cool. So anyway, well, in principle. So yeah, so anyway, this is John. John runs EE. We're working on a cool new product. We talked a little bit about whether or not we're going to say what the product is, and basically, you'll probably figure out what the product is, but we're not going to say what it is. But we're just going to talk about the problems we have and how we do business and stuff. So John, you maybe show your screen and kind of introduce yourself and some stuff about your background, perhaps.
Cool. Yeah. So let's see. Joined the company over 2 years ago now. My background is mostly from a consulting background, working on various consumer products, but also industrial, some military. So kind of done a lot of random stuff. Essentially.
Could you pull up a website, maybe show people the most recent thing you're working on, and then I don't know if are there anything online from your previous stuff?
So this is the last product that I made. I basically was the only EE on the team. This device here is it's a sensor that detects allergens in food. This one specifically detects gluten. So I did all the electronics for it, which was a pretty fun project. Let's see, it's got a Bluetooth radio in it, so it links to your smartphone, where you can upload your tests and share them with the community and stuff. Yeah, really neat product. It's still out there helping a lot of people. So that was a cool one. Let's see.
Yeah. Was it tricky to get the Bluetooth going, or was that did that just kind of work from an EE point of view?
We used the Nordic chip, like a system on chip, which basically just worked out of the box. I had to play around a little bit with the antenna to, get it to a reasonable range. But it was
like a smashing kind of thing.
Yeah, exactly.
Was it a chip antenna or a PCB trace antenna, or?
I ended up just using the chip antenna.
Mm-hmm.
But I've done products where I've made PCB antennas before, which is really fun. There's one product I worked on which was basically like asset tracking type of device. So you'd put it on like transport trucks or whatever.
Right.
Yeah, and we had to. Well, I made the electronics, and we had to mess around with the antennas to try to get the most range out of it.
Was that like 3G or something? Or?
No. So what it ended up being is there was like a hub that was like a cell phone modem.
Yeah.
But then the individual assets would just use like a 430 megahertz radio. Yeah. I think I used the chip from TI on that one.
Yeah, sounds right.
CC something.
Yeah.
I forgot now. Yeah. So and so we try to maximize the range on that. Like when we had one company that was tracking their forklifts around a
Job site kind of thing? Or?
yeah, job site, a big factory. So we needed to get like 2 kilometers out of it or something like that, which is
Wow.
yeah. So
Cool.
a lot of tuning.
And that was just on the like a board level antenna, right?
Exactly. Yeah. Different shapes, different topologies. Yeah. Eventually we got it to work, which is really
Cool.
fun. But yeah, let's see. I can show you some. The fun one was this this webpage here. So we were making these guys here. They're simulators for like simulating explosions. Actually, the cooler one was the machine gun. This guy. So essentially, this started as a propane tank and a cigarette lighter in my garage, and turned into this product here.
Wait, so what is the like? Why do I buy this thing? What's my goal?
So this is used for training soldiers. So what happens is you'll get like the trainer will set up a bunch of these like bombs and machine guns.
Oh, this is why you're going through the under the barbed wire kind of thing.
Exactly.
And this stuff's going on around you.
Exactly.
Gotcha. So you're kind of desensitized to like the battlefield noises. Yeah.
Exactly. Yeah. So we used Zigbee radios on this one. So we had like I designed like a control center. Basically a bunch of Zigbee radio, like Zigbee radio, and all of these had them. And then, you know, the trainer could like press a button when he saw people running close and control it.
Right.
Yeah, so that was cool, but it actually ended up getting adopted by, what's the name? Like big, not General Dynamics. I'm blanking.
One of the big contractors.
Yeah. One of the big contractors. So.
Can you click the other image there? It looks like it's got like a Pelican case and some kind of, is that the transmitter thing?
Yeah, there's the very ugly ID on that we did. It didn't have, and like literally all these circuit boards.
Well, it kind of looks like one of those things that you know, like, I don't know, from the demolition thing, you actually put the C4 on the bridge, you hit that thing, right?
Yeah, exactly. Yeah. So and I mean, there's plenty of other circuits I made for the. I did this timer. This is a company that does IED training, so like how to disarm bombs and other things like that.
Yeah.
That was fun. That was random.
So you had a contract company that would, and then this is one of your clients at some point.
Correct. Yeah.
Cool.
Exactly. So there's what else?
And you did gas meters, and you also did this very like high precision analog data acquisition thing, right? Is that online somewhere?
Yeah. Actually, see if the web page is still up.
There it is, QDAC Systems, right?
Oh yeah, there it is. Yeah. So this. Excuse the I wrote a lot of the stuff in here, but this is what it looked like. It was a data acquisition system. It wasn't very high bandwidth, but it had a really good noise floor. So that was the cool part about it.
This is still being sold today?
It is, as far as I know, although I don't know if too many people are buying it.
Sure. And this is somebody that you had worked with, this company, QDAC Systems?
Yeah, so the company was started by like a former astronaut, Bjarni Trygvason, who sadly just passed away a few months ago.
Oh, wow.
Yeah. So he recruited myself and a few of my, the other person that started my consulting company, that I started a consulting company with. To do the electronics on these devices. There was a senior analog engineer as well. Everyone came over from the Canadian Space Agency, basically. So it was a really good experience because I learned a lot about analog engineering there. Obviously, not enough due to the fact that we have so many noise issues on our current product.
On our stuff here now. Do you know what did you ever measure like the E knob for this kind of stuff?
Yeah, did we measure?
Like doing the FFT method?
Yeah.
Actually, wasn't Steve doing that? Is that right?
Yeah, Steve was the one doing that stuff. Let's see, I don't remember what it was, and I'm sure I could find the data on my old laptop, but we definitely did that. Yeah.
Cool. That's cool.
Yeah, so that was a QDAC.
So actually, I'm curious, like, what does it look like inside that box? Like those connectors there, did those have, were those then wired in with coax to the board, or is there a board behind there?
There's a board behind there.
And then there's another board, or?
So yeah, so there's a board. We had a ribbon cable going to our analog board. I believe
From the connector board.
Oh, wait, no, okay, wait a minute. I'm starting to remember. So there's the connector board. That was a separate board. I should just pull up my other laptop. I think I have all those files.
We'll do the next time. Cool.
Yeah, but it was there was a connector board, and the analog board plugged right into it. There was a board-to-board connector.
Mm-hmm.
Right. Yeah, that's what it was. So we had a separate analog board, and then we had a separate digital board where we had the FPGA, and then we had a separate power conversion board, which basically had all the switchers on there, fed like plus minus 15 volts or something along those lines to our digital board, which then had a bunch of LDOs to condition it, to regulate it down to other voltages, and then we filter the hell out of that. And
Was that plus or minus? Yeah, it says plus or minus. Yeah.
Yeah, plus minus. We'd filter that a bit more, and then pass that over to the analog board for the sensitive analog stuff, separate ground planes, all that kind of jazz. Yeah. And
notice any performance difference with the case off and on, out of curiosity? You know, like you took that big metal case off of there. Was it picking up AM stations and things?
Yeah, the case definitely did help shield things.
Cool.
For sure. Yeah. Yeah, but this is the noise floor here. If that means anything for you. 10 to the negative 12.
So that's sort of like the noise density, right, per unit frequency or something. Then what was the other thing that was on here too? The 1/f noise. So I'm not super familiar with that. Is that's something like at low frequency, there's sort of unavoidable higher noise levels, right? Is that the
universe? Yeah.
Yeah, is that right?
I don't understand it myself, but yeah, I guess so. We need to read it.
Well, there's like the background the microwave background radiation, but I assume that's at microwave frequencies, which is like hundreds of gigahertz or something. So it's probably not that, right?
No.
Then there's also like resistive noise. Yeah. I don't know what it is. You'd think I would, it's like I learned something as soon as I think it might be my problem. I'll learn the hell out of it, right? But like if I don't think it's my problem, I'll just kind of like know that it's out there and like on a shelf somewhere for when it might become my problem.
Exactly. So yeah, I haven't heard this term since working at QDAC. Like
the 1/f.
No one ever mentions 1/f noise. So really, yeah.
Although the op amp data sheets and that kind of stuff, but
yeah.
Cool.
And does QDAC. What else? I mean, the gas meters were kind of cool because there's a lot of since you're dealing with natural gas, there's the whole like safety issue around it. So have to really deal with like protecting your battery and preventing any sort of chance of sparks.
So we were talking about that the other day. So remind me about that. So you had conformal coding. You had
basically
diodes of some kind, or
Zener diodes everywhere and series resistors to limit current is essentially the approach. But they're just called Zener barriers.
Is that like there's some sort of transient they'll short it to ground? Is that the idea?
Yes. No.
Okay. So that the voltage wouldn't get high enough to arc or something at some point. That would be now. Would you actually test that? Do you actually put like 1,000 volts on it and prove that it doesn't do anything bad, or
They do. So you have to go through, like, we were using CSA, which is like a lab in Canada.
they actually did these tests?
Yeah. And well,
Cool.
they start off by, like, you submit your schematics and they have all these tables where they look like the maximum capacity, maximum energy that can be stored on your circuit
Mhm.
versus, so they look at capacitance versus voltage level and so on. And they have these tables and they know you can't go above this certain amount of energy before you like spark or something like that. So
So do you remember like what that capacitance has to do with it? Or,
that's storing energy essentially. So
right.
so what they do is they tell you that so depending on the zone that you're putting your electronics in, they'll say that a circuit is allowed to have one fault or two faults. And essentially what that means is they could take any node on your circuit and like either connect it to ground or like short it or whatever, right?
Sort of to a DC voltage or to ground.
Yeah, anywhere they want. They could apply a fault.
Okay.
And same with like any component, they could just like say, okay, this resistor now is a short. Or this,
interesting. These two nodes are now shorted together.
Exactly. And so if you have like a lot of capacitance, that can obviously store energy. And if you short it to the wrong place, you can get a spark.
Oh, so okay. So you get a lot of current that,
Yeah.
So gotcha. So it's really high impedance and there's no stored energy. Who cares if you short it out? But if there's a big cap there, this got 10 volts on it and you just shorted it to ground, then you get like 50 amps or something. And or interesting. Cool.
Yeah.
That totally makes sense.
So yeah, so basically they go around your schematics and just see if you're breaking any of those rules. And wherever you do have like you know, too much capacitance or whatever, you apply these Zener barriers usually in those places. So you put a Zener diode, and then to protect the diode, you put a series resistor in it, and hope that that doesn't affect the functionality of your circuit, which a lot of times.
What does that? What does that look like on a schematic? You know what I mean, like.
Well, you can buy them like this, but basically, yeah, these are all like ATEX approved Zener barriers, but yeah, sometimes you need a fuse on it, but this is essentially what it looks like.
Where would the cap be?
On this side, sorry, this is backwards.
The safe area to the input area.
I was discussing like
yeah, so the cap would be on this side on the right.
Oh, the input side. Okay.
Yeah. You can also have like galvanic isolation. Yeah, just trying to find
Capacitor example.
Yeah. Right.
Yeah, don't find it right now. It's okay, but
so software in a VM, depends on the host and guest log situations. I've never seen it work.
See if this brings anything up.
Seems to work okay most of the time on Windows host and the local performance settings.
Not
And then
really.
your deal is
But anyways, yeah, if you look at the standards, it's all about how much capacitance you can have on the board.
yeah, I mean, it sounds like they can reduce it to a series of like rules that you either violate or not, which that's obviously very helpful. But rather than having to sort of reason through it all, right? If this, then that would become pretty unmanageable, right? This kind of reminds me of our reset circuit, right? Like there's too many different stakes to track.
And there you go, high value capacitance. Oh yeah, and we had to have, I remember that, you had to have like really thick trace, yeah, depending on the zone. You have to
say unfailable? Like you can't fail, is that what it means?
Exactly, yeah. So you had to put peril diodes in place, just in case something goes wrong with one. And then you had to use these like really thick traces to connect them. And
Gotcha. So if they start dumping current, they're not going to fail there.
Yep. Yeah.
Cool.
So that was
Good times.
interesting world.
Yeah.
Yeah.
So you had this up actually. Well, there's a lot of stuff we could talk about. Yeah. Maybe talk about like, okay, so we use GitHub to do Altium, at least for now, right? And there's a whole Altium 360 thing, and we're not really 365. But I'm never sure if it's 360 or 365. But anyways, but anyway, for the time being, we use GitHub, and we have a certain folder structure, right? Maybe you can pull that up for one of our things, just like the GitHub folder structure.
Sure. Well, let's see. Sorry.
Yeah, I think it's that Logic IO PCB.
Yeah.
Xilinx.
Yeah. So we basically have the project, the PCB, the schematic folders. We also have releases. Once we release something, we basically put the zip file there, and then your job file, so your output, like Gerber output file, and so on. Yeah. So we keep this structure, and then just throw all that up on Git, and every time, like, we have multiple people working on a board, we just communicate and say, hey, I'm checking the board out today. Don't make any changes, or else we're gonna have to deal with contentions.
Exactly right.
Yeah. But it's been working great. I mean, we have all the records of everything we've done. There's been several times where I had to go back to a certain layout or something like that.
You're trying to figure out what broke when.
Exactly.
Yeah, and it was cool too, is you can like tag when we release it, you can tag that, and
so it's like, what did we do on each one? Just type that into Git, right, and get the release, download it. So it's and we also keep our library in a single
right, the GitHub repo. That's sort of I forget, it's called, like, it's like what's it called, a GitHub sub module or sub something. So it's just kind of automatically included, if I recall correctly, in the. Is that right? It's included in the different projects.
Yeah, well, yeah.
It's not like you don't have to download it separately and then like link Altium to it. I actually don't recall now how we're doing it now.
Yeah, I mean, you have to, anytime when you make updates to it, you obviously have to download it, make your changes, and then compile it. But all our projects are, well, all the projects in the new product of these automatically reference that library. So
cool.
It's convenient, yeah.
Cool. So actually, now that we had the Altium up here, maybe you can kind of show us a little bit. So this right here is what the digital board.
Yeah, this is a digital board, and I was just reviewing some of the routing on some of the USB, like LVDS and USB routes, the length matches. Yeah, trying to avoid this sort of skipping layer thing.
Yeah. What are those USB lines there?
Yeah, they're the SerDes lines.
Right. Yeah, exactly.
Yes. So yeah, we got a bunch of them, trying to length match them all. And obviously one goes way up high, so
so I'll just
makes it complicated.
my recommendation is definitely do this top one.
Cool.
Yeah, but this is
can you pull it into the 3D view? Just for fun, give people a give me a picture.
Yeah, so this is the digital board.
You go ahead and maybe just walk around and say what all the different parts are approximately.
Yeah, so the big chip, FPGA, USB controller on the other side. This is kind of similar to what I was describing about the QDAC system, except much faster. basically here is just all the power circuitry to support.
Yeah, so that's a PMIC, right?
Yeah, that's a PMIC. And that's the main thing on this side of the board. We have some board-to-board connectors that go to the analog board. We have our DDR, SODIMM, and then just
Is that mostly P? Oh, that's the I2C switching thing, and then we have the CC.
yeah, these are the PD chips.
PD, right? Sorry.
Yeah, power delivery chips, and then just some normal switches to like so you can cut VBus to your USB.
Oh, that's right. Turn off the power, right?
Turn off, yeah, turn off and on the power. And, yeah, let's see what else. The same. There's like a PD controller for the PC, the wall power.
And on the top right there, gray, that's that clocking.
This is the clocking chip, yeah, which goes both to the for clocking the digital stuff, but it also clocks the analog, the ADC,
Right.
which is on the other side. I mean, the other board, the other board, yeah. And then on this side, it's basically all passives, you know, your caps, bypass capacitors and stuff.
That a ridiculously large inductor back there.
Yeah, this is the main 5-volt supply,
Yep.
which we expected to have to be go very high. I forgot, like 10 or 12 amps or something like that,
Mhm.
right?
Yeah.
Yeah, that's why it's so huge. But we have so much filtering on it that once it gets to the analog board, this rail is actually
Yeah,
pretty clean.
it's interesting, like how we have very few problems, all things considered, but the ones we do have, we're kind of stumped on.
Mhm.
Uh,
Yeah, that's on the other board. I can pull up the other board actually.
Yeah.
I had it up here. Yeah.
So basically, the problem we're having now is, without going into the super details, is we have a high impedance analog front end, and it's picking up noise from two of the negative rail switchers.
Yeah, so yeah, we have a front end that has some relays for attenuation, and the relays seem to be picking up the noise. Interestingly enough, it's not picking, there's multiple switchers on here. There's some positive rail ones, and that noise is not showing up in the FFT, but the negative rails are showing up.
Yeah. Now, then this is also when, you know, like very high impedance and very zoomed in. Like there's a variable gain amplifier, and it's like, so it's not like a huge effect, but like
No.
it is noticeable if you're zooming way in.
Exactly.
Um,
And
Now we have removed the relays, and we know the relays has a kind of a wire loop in there that, but even removing the relays, it doesn't make it go away. It's not like some magical thing. Like if
No.
you short the relays over,
Yeah.
you're still picking it up.
yeah, it's still picking it up, just much less of the noise. Like it's almost gone when the relays aren't there.
Yeah.
Um,
And the other interesting thing is this obviously has a big shield that goes on the top of here.
mhm.
That shield has no impact on this.
Well, it actually makes it worse.
Makes it worse, right?
Yeah.
So, which that's definitely a big clue, right? So, I mean, and Mark points out immediately, well, then it's like magnetic coupling or something as opposed to like RF,
Exactly.
which I'm not exactly the EMAG expert on like, anyway, but yeah, so, and then what else is there to say about this issue?
So I mean,
We've tried a bazillion things.
yeah, I mean the fact that it's the negative, like we're using buck regulators set up in the negative topology.
Yeah, maybe you could open up that one of those files.
Yeah, so the fact that it's the negative ones giving us the problems is interesting. And it seems like it's because that like the ground is bouncing around or something like
Yeah.
that. But yeah, like the positive 10, you know, also switcher, super close to the analog circuitry, filter a lot. It's
Right.
not getting,
Zero impact.
yeah, zero impact, but we're not picking up like magnetically or in RF. We're not picking
Right.
up the switching frequency, but we are picking up the -5 and the -10.
Right.
So yeah, so I'm investigating like trying different layouts, trying to minimize the loop. Learned that actually in this topology, the input capacitor is the most important. So I started simulating this stuff, and like you can see where the current goes. Let's see. Yeah. So
By the way, normally we'd be using LT Spice, but John, I guess the TI has like this P Spice.
yeah, so I
Is it
couldn't.
is it fully featured?
Yeah, no, I don't think that you get all the features. But although I'm not sure about that actually. This is like the second day I've used this. Normally I do everything LT Spice, but unfortunately TI encrypted these models, so you can't use them in LT Spice. At least I don't know a way of using them in LT Spice. So I just downloaded the P Spice that they provide, which is all right. Like so far, I've like I can do all the simulations. Then you can take your like current probe and like if I want to know what's coming through this inductor, place it. Oops, place it. Yeah, place it in the right place. Go to my simulation and whoop, there's the inductor current right there.
Gotcha. So what is that then? If you zoom in on that, what's the kind of?
So unfortunately, the like capabilities of being able to zoom properly in here is like so bad. I think the best way of doing it is
I'll use that that plus thing at the top of the screen, that magnifier maybe.
Yeah, but then
God, never mind.
Yeah.
Is it marquee select, like maybe the
So I can do this, yeah.
There we go.
There we go. So you're seeing here.
So this is like 800 milliamps to 600 milliamps, something on that order, right?
Yeah.
So it's and then what? So is it the purple?
Yeah, that purple is the inductor current.
Okay, so there's a big DIDT right when it switches direction, right?
Mm-hmm.
In fact, could you zoom in on it even more, just like look at one of them, like one triangle wave? Like, is it? I mean, I don't know how good the simulation is here, but you wouldn't think you would be so sharp. Well, I guess it is. And what's the little pink line?
So that's the current going into the. That's the.
Is that the derivative of it, or?
That's this guy here, which I believe should be the same as current in this capacitor.
Well, that's what I'm confused about, because we have one cap going to ground and one of them is going to the -5 output voltage, right?
Yeah, let's take a look.
And then server is a little bit missing.
What happened to the other one? What color was the other one? The other one's flat.
We just load this TLL.
Which other one? Sorry. Oh, the
Yeah,
the ground,
C2.
the ground reference one.
Yeah.
Just exposes functions like create a graph.
So the one that's hooked to ground is like has like minimal DIDT in it.
Exactly.
Okay, gotcha. So -501.
Yeah.
Oh, the yellow one's that one that's super peaky.
So yeah, the one that's connected to the negative, like our output,
Yep.
or -5, has a lot. This one here is just constant.
Yeah.
Yeah. So it seems like I want to be focusing on minimizing this loop here, going through this cap.
Yeah. So right.
Right, not the other one.
Okay, so if you zoom out here, like so part of the loop, I guess where exactly is the loop, right? Like if we were to like highlight it on the screen, obviously part of it is that capacitor C2. That's part of the loop. Part of it's is part of the loop going through the chip, or is, I would imagine so. You know what I mean? It's not.
Yeah, so I mean, it looks like all the current is coming through the capacitor, I mean, through the inductor, right? Down through the output capacitor, which is here. Does that make sense? Well, no, not really, because that's, yeah, let's take a look.
Exactly.
In here.
So what I'm gonna do right now is,
There's a lot of current in here.
this is just gonna, this command does one thing. and
Yeah.
this, uh,
Same as the input. So this has a lot of switching current. This has a lot, and then it looks like it comes back through here. Right?
Yeah, this is something we'll need to work out on paper more, but you can imagine, I mean, this is like pretty classic circuits where essentially all the sum of the currents need to be equal to what, 0 or whatever,
Yeah.
or however that works. And
Chris knows a lot. Yeah.
but you know what I mean, like they all should add up. So whatever the heck is in whatever's going through C8 must be the sum of the two wires coming into the top and the two sides there, right?
Yep.
And then same thing, anything coming out the other side of this chip, they have to add up to that coming into, you know what I mean? So anyway, we can kind of figure out like how it's distributed, like, anyway, the thing we're concerned about, so obviously we can have a very tight loop. So I guess there's two open questions, right? One is like when you have, maybe you could pull up the layout. What do you want? So I guess the idea is to minimize the loop area, right?
Yeah,
And
this is a bad layout. I made a
right.
I made a little
Pull up that other
adapter
board. Yeah, yeah,
And
that.
yeah, so this one I'm trying to minimize that loop area. So you've got like, you know, your inductor going through the output capacitor straight back into the pin, and then your input capacitor is here. That goes to ground. And then here's that other capacitor that we should be worried about. So I guess, according to that simulation, our loop is actually this whole thing here, right?
Yeah, well, it's not obvious to me right now,
Yeah.
but yeah. So I guess there's a couple of questions. One is, does the fact that we're using plane actually reduce the loop area because the current at high frequency or whatever is going to pull into the inside of those planes, or is that irrelevant first, right? And then the second is the fact that we're using planes causing more of the issue because it's acting, it doesn't seem to me like it'd be acting like an inductor to, anyway, we read somewhere kind of anecdotally that having a plane is not necessarily the best policy.
No, what did they use the term, like a radiator of some
Yeah,
sort?
exactly. But it's not clear to me that it's not just an RF radiator, which isn't our problem.
Mhm.
You know, I mean, if it's just kind of some sort of broadband antenna sort of a thing, that's not our problem.
Yeah,
So anyway, so that I guess anyway, those are the two questions about the planes, and then I think the critical question seems to be, where exactly is the loop if we were to actually draw it, and then critically, what does that loop? Because the loop theoretically goes all the way back to the battery, so to speak, or back to the power plant, right?
mhm.
Now it's not the whole power plant, obviously. That's our loop. So I think the reason our loop is more local than that is because it's decoupled, right? And in fact, you can see that there's very little current going through that C1 there, or whatever that one is. So anyway, to what extent are we decoupled? Or what extent is our DIDT actually extending through our planes, going all the way back to some other supply, right? Like that's really critical. If we could isolate our DIDT to be local to this circuit and to our little loop here, that's a way better situation than if it's sort of rolled out over the board, right? Anyway, we'll solve it right now on this call, but it's just like a really fascinating thing.
Mhm.
What are the different things we've tried?
I mean, we've pulled the inductor right off the board because first we're like, oh, it's all in the inductor.
Yeah.
And, you know, put it on
Shielding
long
for that.
wires, shield, like twisted them, put them, and that didn't make a difference pretty much at all. We tried shielding, we tried magnetic shielding, which did make a difference, but I couldn't eliminate the noise.
Yeah, it's very unclear to what extent we're actually providing the complete flux line thing, as opposed to like throwing some magnetic tape crap, you know, and
the interesting part about it was like, you know, I told you that once you put the shielding on, the problem got worse.
yeah,
When I had the magnetic shielding material on the inside of the enclosure, when I put it back on, it didn't get worse. It stayed the same.
right.
So that was interesting.
Yeah.
What else? I tried basically taking 2 of these boards and, you know, powering the plus minus 5 and 10 off a second board. And that seemed to have fixed it, remember?
The negative 10, the negative 5.
Yeah, negative 10.
When they came over from either an external power supply or the other board,
Yeah.
issue was gone.
Yeah, the noise was gone. Also switch, unless you took that ground wire and put it near the, I guess any wire. It was, you were the one that was playing.
Right,
with
right.
the
So
wires.
the wires that were coming over had DIDT in them, theoretically, whatever. And you put them next to the sort of the high impedance bit of the circuit, and it was definitely picking that up.
Picking that up, but when it was away, it was fine.
Yeah.
So that
So
was
one of our questions is like, when we do a more significant, we're considering doing a very significant redesign of this board because of supply chain nonsense as usual. And I mean, obviously this product's pretty far from being launched, but we're trying to bring it in by switching to a different chip, blah, blah, blah. But we want to obviously move these supplies to the other board. But to the extent that they're magnetically coupled, all of our crazy shielding isn't going to, and so now that, I mean, it's still like an inch away.
Yeah.
Even though it's on the other board, so we really kind of got to crack it really understand what we're doing, I guess, before.
Mhm. I'm also looking at other topologies at the.
Yeah.
So I made these little adapter boards, right? And then they solder right onto it.
You probably never worked on web applications. So this is
Let's see, they solder right onto the.
Yeah, maybe stop sharing here for a second so you can kind of zoom in better.
Oh, yeah. Stop share. Yeah, so they solder right onto where we have the switchers. I don't know if you could see them right here.
Yeah.
So I was trying different layout approaches, but also I can try different topologies that way. And kind of
Basically, you built this little circuit board that had like the tightest layout of all time, theoretically.
Yeah.
Put it on there with like 3 different connection points.
Yep.
To the main board.
Just ground and power.
Surface mounted it on there, and noise is worse.
Yes.
Yeah, so that's just like.
Yeah. So the next move is to try this, the CUK topology, which is supposed to have lower noise. So I just got a dev kit for this.
So what it does for sure is that there's no DIDT, so to speak, in the input or output, right? Like those are very clean, but does it actually have lower DIDT in the main switching elements of it? I think the answer was yes. The other thing that seems to be related to this is these are buck topology, buck in an inverting topology.
Yeah.
Which has, I think, much higher DIDT than you normally would see, I guess. And somehow that's related to this.
Yeah.
Want to share your screen?
Oh, sorry. Yeah.
There's a bunch of stuff that can't actually be done inside the render context. It has to be done in the main context.
Yeah. So
A little bit I can see too.
so these, they have, you know, continuous, the main advantage is continuous current at the input and output of a converter.
And much higher currents inside the I guess on the MOSFET or something like that, but.
Mhm. What else? It does talk about why they're lower noise somewhere in here. In any case, yeah, I'm gonna try this topology, see if it's like I tried the dev kit from TI and hooked it up to our board, and I wasn't picking up any of the noise, but obviously it was off the board, which
Right,
our switchers off the board did the same. So now I want to try it right on. So I made the little
Right.
adapter board, and I'm waiting for the parts to come in. Digi has stopped shipping stuff.
Yeah.
That was weird.
What did they send you? Something that said like that.
Yeah, they're like, your order was affected by, your orders have not shipped because we are moving to our new building. It seems like your order was impacted by the transition.
Yeah,
So I don't know when it's going to be unimpacted.
exactly.
Yeah.
In the early days, we actually had the
Yeah.
the electron out. This is all.
Anyway, so
There was an extremely brief period where people
yeah, that's what I'm trying to deal with is these noise issues. But I would love to understand,
with the browser.
like,
Can you give me one thing really quick? You look at the current out of the battery. You know what I mean? Or I'm sorry, out of the 5-volt thing right there, right?
mhm. Let's see, orange.
So so that's the logic directory, and then this last one here.
Is that really true?
This exists as a separate package.
Okay, is that okay? So that actually might be so.
Sharing code, please.
Check it out. That's not isolated. Right? That's actually the battery, right? That means that loop is all the way back to the power supply.
Yeah.
That's what I was thinking about, right? So why is the
So what you're saying is, in like our actual board,
So we have.
what you're saying
if
is
you put
that
like go ahead. Yeah, from the 2 injection points all the way back, there's DIDT
like
at that point.
up here.
Well, I have no idea. I'm not really sure. Because like if you add more decoupling, does that get rid of that? Because if you go back to your LTs to the eSpice sim there, like you had that really big cap.
This guy.
And yeah, I guess I don't really understand what a cap does when it's directly across a voltage source exactly. But you can imagine having an LC there. If you put an L like there, like there's no way you're going to have high DIDT on the battery at that point, right? Is it like
So we should have some input filters here.
Right, exactly.
Yeah, like,
and you could do that on your dev board, on your little.
yeah, I have to make a new dev board. I was trying to actually do that on the, because we have some other filtering, but I couldn't find a place to stick the L.
Right, because there's a bunch of planes and things.
Yeah, exactly. So I do need to make some more adapter boards and see if that's the problem, if we need to filter out or.
Well, you could just, you could put obviously you could put it in the sim here and that should go to 0 as long as the cutoff frequency is below the, that effect we're seeing. So, yeah, that did come up. We did talk about that, right? We normally have some kind of LC on the input to the switcher and we didn't on these, right?
Let's see. Well, we do have some filtering. So these are getting powered by the 5-volt rail. We don't have an L. We only have some large caps in one of these feet.
On the 5-volt, right? Well, that won't even matter though, because like it needs to be filtered locally for the journey to be low frequency too, if that makes any sense.
Yeah.
So in other words, like the LC needs to be right on the left side, right here, right?
Yeah,
and normally
right
we
here.
would have that there. Because at that point, like everything to the left would be low frequency, right? Whereas if you put the LC way over somewhere else, all that path will be high frequency.
Exactly.
I would imagine, or that's how I would mental model it.
I think so. So yeah, what I wanted to do.
Oh, we tried that, but
no, I wanted to try to put an L in here, but I just have nowhere to do it on the current PCBs.
Right.
Like close to this chip. Unfortunately, it's all, it's routed on the inner layer.
Yeah, yeah.
5 volts. So unless I start drilling vias and stuff like that.
Right.
So yeah, that's a good point. I need to make some other adapter boards and see if I can, if I add filtering at the input, that's going to help our situation.
I could see that.
Yeah. I mean, let's see. We just,
You know what you could do is that little board you have has 3 connection points, right?
yep.
So you could imagine like having like 0 ohms standing up off the board, off the main board, and
Okay.
L standing up on one of them, and then solder it to that little 3-prong structure, you know?
Yeah, yeah. So just put a bunch of 0 ohm resistors in one.
Yeah, like
L.
ideally like 0805 or something like that, ideally, right?
Yeah.
See
See this.
So the way you get these 2 repositories and the way we kind of sync them together is as
There's already a C there. See what this does. Oops.
And this file
Zoom is
contains the commit ID of the graph
Zoom is
build
blocking my
software.
run. Oh,
This is a huge development.
that was
That's weird.
Push change to the back end. It just builds the CI. That takes like 30 minutes. Once it's done, you can paste that thing in here. And now you build either a local development or you build a package and ship it.
Try that.
It'll just download that out.
There we go.
The assets.
Well, that's going to take a little bit of time. Anyways,
And that's how we do.
That's fun.
Today. It's like, okay, once we the testing.
Yeah.
Cool, yeah.
what else?
You probably stop the transient analysis, right? I mean, we only need like the first cycle, right? I mean, I'm just making that up. I don't.
Yeah, I mean, the first, it'll just start showing up and then we can pause it.
Oh, okay.
Here it is.
So we're really focusing on how to make that build.
What are we looking at here?
Happened? Well, apparently we messed stuff up here. Here's our V out.
Okay, this is just like early in time. That's all, right?
Yeah, I guess so.
This is microseconds, yeah.
Resume.
Okay,
Anyways, we'd have to take a look.
cool.
Yeah,
Okay.
I didn't really think about what I stuck there, so I have to take a look.
Let's see what time is it? Cool. Well, we're kind of out of time. This has been fun, though. And maybe we crack this. We'll see.
Yeah. Well, we will.
Yeah, definitely we will. Yeah. And if anybody knows anybody or is a expert on sort of magnetically coupled noise for high precision analog, that would be super great to hear from you.
Yeah, for sure.
So
Get a lesson in this stuff. That would be great.
yeah, exactly. Yeah, we can't afford it right now, but we dream of the day where we're gonna have this mythical analog guru on staff who's gonna be able to do crazy analog front ends and you have kind of like a little universe, like basically teach us, so that we really know what we're talking about, which would be awesome. But all in good time. I gotta make some more money first. So. Hey, all right, John.
Great.
Thanks a lot. We'll talk soon.